So on this version of the quiz, I'm using some of the same functions from one of the versions that you took, but I've changed the actual number. So the answers may not work out quite as nicely, but it'll give you some additional practice. The key to dealing with composition of functions is just to patiently write the problem in terms of nested functions and work inside the parentheses out. Same way we do any kind of algebraic computation, we work inside the parentheses out. So inside the parentheses we see g of -5, and so I want to replace that with whatever g of -5 is equal to. So over here on the side I can figure out g of -5 is what I get by putting -5 in for x in this expression. So if I do that, twice -5 plus 1 is -9. So g of -5 is -9. So I replace g of -5 with -9. Now to finish the problem I need to know what f of -9 is, and so that means I have to look at my f formula and put -9 where the x is there. So replacing the x in the f of x formula with -9 will give me -9 over -10, which is just positive 9/10. In the second problem, we put it the same way, so I rewrite this so that it looks like nested functions. First thing I have to know is what is f of 3, so I'm going to replace f of 3 with whatever f of 3 is equal to. To find out what f of 3 is equal to, I come over here. F of 3 is 3 over 3 minus 1. That's using the f formula again, changing the x to 3. And this is 3/2. So instead of g of f of 3, this is g of 3/2. Now I have to turn my attention to the g function and figure what that is. So the g function says I should take twice x, here x is 3/2, plus 1, that's 3 plus 1, which is 4. In the second problem, I'm doing the same sort of thing from a graph, but I do the same steps. So I rewrite this as nested functions. F of g of 1. Again, I first need to know what g of 1 is, so I'm going to replace g of 1 with what it's equal to. And to do that, I need to know how to get g of 1 from the graph. G of 1 means look on the graph of g, there's g, look for the input being 1, the input is the x-coordinate, and find the point. So here's the point on the graph of g that has the x-coordinate of 1. G of 1 is the y-coordinate of that point. So the y-coordinate of that point is also 1. Since this is the point 1, 1, that means that g of 1 is equal to 1. So f of g of 1 is the same thing as just f of 1, because these are equal. Now to find f of 1, I look at the f graph, and I play the same game. I know the x-coordinate, the input should be 1. So I'm looking on the graph here, and I can see that the output, the y-coordinate for that point, is 5. So f of 1 is 5. So this is my answer. Same thing here, nested functions first. Find f of -3. First, f of -3 means I look for the x-coordinate to be -3, and I'm looking on the graph of f. So this point right here is the point that has input -3, output +3. So according to this point, f of -3 is equal to +3. So don't forget that the x-coordinate is your input, the y-coordinate is your output for your function. Now to find g of 3, I have to look on the graph when the x-coordinate is 3, which you know I've written all over it. X-coordinate is 3, I need the y-coordinate. So unfortunately I made up a problem where I don't have a nice dot there, so I'll have to just estimate. So in this case, 1, 2, 2 and, I'd say 2 2/3, 2 1/2, something like that. So I'll say it's approximately approximately 2.5. But it should be the y-coordinate of that point. So on the G graph, when the input is 3, the output is about 2.5. In the last problem, we're forming a composition algebraically, but I don't do steps that are any different. So I'm trying to find an algebra expression for f of g of x. So I rewrite that first as nested f of g of x. G of x is replaced by what g of x is equal to, same as we did before, but g of x is equal to 9 minus 4x. And now I have to apply the f function to that. The f function takes the input, whatever input you give it, and takes the square root of it. So if you give f the input something more complicated, it's just going to return the square root of that more complicated thing. So this is your algebraic formula for f of g of x. The domain of this is going to require that the stuff under the square root sign, so anytime you have a square root in a function, you're going to have a domain issue. Something to check, you need the stuff under the square root sign to be at least 0. You can't take the square root of anything that's less than 0. So to figure out the x's that'll do this, the way that we were talking about doing it in class was to first figure out where 9 minus 4x is equal to 0, and then just check to see if higher numbers are good or higher numbers are bad. So this equation has solution x equal 9/4, if you were to check it. So that means by putting 9/4 in for x into this formula, you're going to get the square root of 0. And so if you move a little bit away from 9/4 with your value of x, you may get a negative number. You may get a square root of a negative number. So the question is, which way is a good way to move and which way is a bad way to move? So to check that, and we'll be doing more of this later in the course, you can picture a number line. So there's a number line, 0 is there. 9/4 is 2 1/4, right? So 1, 2, 3. So 9/4 is right there. Okay, so 9 minus 4x is 0 when the value of x is 9/4. So now let me check what happens when I use x equals 2. 9 minus 4 times 2 is equal to 1. And so that is greater than or equal to 0. So it satisfies that inequality. So I can put a little check mark here. That's a good thing. And so I'll have check marks all the way down here. The reason I only have to check one value over here is that in order for you to have a transition from positive numbers under the square root sign to negative numbers under the square root sign, you would have to actually be 0 under the square root sign. And we already figured out that this is the only place that you're going to have a 0 under the square root sign. So if something over on the left side here is okay, then everything over here on the left side is going to be okay. So let's also check what happens when x equals 3. 9 minus 4 times 3 is negative 3, and so that's bad. Remember, I want to have the square root of a positive number, so the square root of 1 was fine, square root of negative 3 is bad. And so these are bad over here. Bad, bad, bad. So you write happy faces or sad faces, or just some people write pluses and minuses, right? It's a little more neutral if you write pluses and minuses. Because pluses are good for square roots, minuses are bad for square roots, so that works out okay. So we can see from this analysis that the values of x that are good are all the x's at 9/4 and smaller. So x less than or equal to 9/4 is one way to say it. If you want to use an interval notation, you would say minus infinity to 9/4. And I guess I'll answer my phone.